Hello everyone, I'm Runjia.
I'm Yujie.
Today we are presenting our technical paper, Performance-Based Midsole Design Using Computational Multi-Objective Optimization. Additive manufacturing, also known as 3D printing, has been broadly applied to product prototyping and fabrication. With the advancement of data science and volumetric modeling toolkits, there are opportunities in the footwear industry to employ computationally generated lattice systems in place of conventional components and materials in order to enhance performance with new design possibilities. Located between the outsole and the midsole, the midsole performs as the main cushioning, stability, and pronation control component. Midsole materials, subcomponents, and overall composition determine the quality of the running experience. And thus, many running shoes end up featuring a broad range of midsole components and materials. Data-driven computational design offers opportunity for personalization of this process.
There have been many explorations of underfoot pressure data as a primary form factor. In recent years, New Balance partnered with Neural System to develop 3D printed midsoles for performance running shoes, in which the 3D printed lattice geometry was determined by pressure data. The project presented below challenged this conventional footwear data usage by proposing a new design agenda that treats RMS data as the primary form factor and pressure data as the secondary factor. We see an opportunity to add on to this data-driven approach through taking the temporal implications of running into consideration. Various parts of the midsole come into effect during various parts of human movement, and this can be used to inform lattice distribution and structural units design.
For this project, we propose a systematic workflow composed of 3 parts: ideation, data-driven design, and multi-objective optimization. The ideation process is composed of 2 hypotheses: the hypothesis about system global performance and data type of interest, and the hypothesis about unit local performance and quantitative properties. The data-driven design approach is composed of data acquisition, temporal data clustering, midsole segmentation, and unit choice. And the outcome for the data-driven design approach becomes the input from multi-objective optimizations, which is composed of design space exploration, performance simulation, prototyping and fabrication, and segment blending. The first step of the data-driven design approach is the data acquisition. The performance-based midsole design starts with ideating how available data types affect the running experience. There are 2 types of data that we use in this project, both obtained from New Balance. The underfoot pressure data, which reflects load distribution, and the RMS data. The RMS data reflects surface deformation in the running process across time. Due to its sequential nature, this RMS data makes it possible for us to track midsole's behavior over a specific time span. The second step is data clustering. Data clustering allows us to understand the behavior of different zones of the midsole and come up with different data interpretations to inform various types of design. We apply the deep temporal clustering algorithm, which is a multi-layer neural network, and a K-shaped cluster algorithm together to determine the optimal numbers of clusters for segmenting the midsole into various parts. With 100 frames of displacement and strings, the data was segmented into 4 to 8 clusters, depending on their strings temporal pattern, calculated by the temporal clustering and the K-shaped algorithm. The optimal number of cluster, 6, is selected with validation. Then we took the 6 optimal zones and tested them with various proposed optimal lattice units to be distributed in each segment. Various lattice units were picked to suit the temporal pattern, ranging from an auxiliary structure that provides cushioning and bouncing to a solid minimal surface structure that provides resistance in the pronation process.
In our computational multi-objective optimization phase, design space exploration approaches the agenda by making iterations with selected design variables. We control form factors of the lattice system and focus on the performance of the lattice unit with two variables: the internal form factor, which is the scale ratio for compactness, and member diameter for the sake of manufacturing feasibility. Performance simulation approaches the agenda by setting up multiple optimization objectives and searching for optimal unit cell design. We treated auxiliary units as beam-like structures and gyroid units as shell-like structures. Finite element analysis is implemented here to quantify the displacement of members of the lattice units when being applied to the same load. Prototyping and fabrication approaches the agenda through making one-to-one partial prototype with resin 3D printing. This helps understand the actual material performance and behavior through physical impressions and simple material tests. Segment blending creates a smooth transition between segments by tuning material density and blending the unit cell structure. The blending factors are associated with the characteristics of adjacent segments.
The Midsole design uses a lattice system as a flexible structure, as this system could be easily deformed and remapped. A variety of lattice units were tested, starting from the auxiliary structure of various form factor and member diameter, to the shell-like solid minimal surface structure that provides resistance in the pronation process. We have developed multiple design outcomes and evaluated them with our metrics. After multiple rounds of design iterations, we chose to design with the best performance as well as the best aesthetic quality.
In this project, we used Aramis data, reflecting distinct surface deformation characteristics as our primary design driver, instead of average pressure data. We proposed a data-driven workflow for Midsole design. Our approach demonstrated how to use deep temporal clustering for analysis of the sequential pattern of running experience and segmentation of Midsole areas. We developed a multi-objective computational system for Midsole design optimization, and we employed computational simulation to make informed decisions to iterate our designs. We developed a method for blending lattice units with different topological configurations. While computational optimization tools become central in decision-making processes, human interventions become even more crucial for setting and running such systems in efficient and intuitive ways. Reminiscing the challenges of blending visual and performative design goals in this project, we find that subjective decision-making, such as visual choices, cannot easily be quantified. Yet still, such decisions remain significant for design exploration. At the end of our presentation, we want to express our gratitude to honor MIT Department of Architecture and New Balance R&D Innovation Students' general support. Thank you for your time.